Welcome, everybody. My name is Philip Van Wassenaer, and I would like to start off by thanking the ISA for the invitation to speak here at the conference today. I think, like many of you, I wish that we were not looking at each other through a Zoom screen and pre-recording, and we were all actually together. But I will assume that you're all standing in front of me in the room, and I'm very pleased to be able to present today. And the topic is assessing and managing aging urban trees. We'll start with a little bit about myself. My name, as I told you, my name is Philip Van Wassenaer. I like to say I've been hanging around trees since I was a little kid. This was when I was 7 years old, and I took that passion for climbing trees into a little bit older in my life for a long period climbing rocks all over the world, and was very pleased to discover that that wasn't a waste of time and that actually I could get paid to climb trees. And so I climbed trees for a period of time. I was fortunate enough to go back to get a master's degree in urban forest conservation. And for the last 22, 23 years, I've been working pretty much solely as a consultant. I still climb trees here and there. And one of my passions really is working with old and aging trees. And you may have seen me give talks before on that subject. You may see some similarities here. But the focus today is using advanced tree risk methods to inform conservation planning for old and aging trees. And as I mentioned, I have a particular focus on that, and I believe that for many reasons we should be keeping the largest and the oldest trees around us as long as possible. As I'm hoping most of you know, the landscape for guidance for tree risk assessment changed in a significant way in 2011 when ANSI put out the A300 Part 9, which was standard practices for tree risk assessment. And ISA, to our great benefit, always puts out the companion documents, the best management practices document, which you see here in its second edition from 2017. And in that document, it lays out, when we're actually doing risk assessment, it lays out a two-part matrix that considers the likelihood of failure, the likelihood of striking a target, and the consequences if impact occurs. And so today, really, I mean, my opinion is that one of the most challenging things about that process is step one, which is looking at the likelihood of failure. The guide also outlines 3 different levels of risk assessment. And they're specified here. Level 1, which is a limited visual assessment that could be a drive-by or a flyover, a utility corridor. When you're really starting to do something more substantive, you get to level 2, the basic assessment, which requires a 360-degree view of the tree, looking at all sides and taking all things into consideration. If during a level 2 assessment, and I think this is a really important part of the standard, it implies that if you see something from the ground or a feature of the tree which you don't think you know enough about in order to inform the risk assessment, you should go to a level 3, which is described as advanced assessments. And that's really where I'm going to be focusing in the front end of my talk here, and then taking those techniques and giving you a couple of case studies how they've been applied in the conservation of trees. So if we look at how do we actually do these assessments, tree risk assessment, limited visual assessment, level 1 is fairly obvious. We're looking, we may be looking very quickly and very cursory, and we can only see, sort of blatantly obvious risk issues with trees. With a level 2, we are going to do a much thorough examination, and we may use some simple tools, things like binoculars or a magnifying glass, maybe a probing tool to look at cavities, certainly a mallet or a hammer for sounding, and sometimes we may dig around a bit at the base of the tree. But that's about what is the level of expectation, and let's say that's the most common risk assessment level that's applied. However, as I mentioned before, if you see something, you may want to or should probably avail yourself of some of these advanced methods. So we could look at things like that are highlighted at the bottom here: root excavation, aerial inspections, measuring the lean, trying to detect decay in the tree, perhaps a wind load analysis, and there are others. So the first one I mentioned was looking at the roots, and we have some very useful tools that are minimally invasive or damaging to the tree, such as this air spade or air knife, where we can blow away the soil and see what's going on at the base of the tree and expose its roots. We won't be doing this for a risk assessment under most circumstances, but this shows what the tool is capable of. This is actually a tree that was part of a research project that I undertook at the Tree Biomechanics Week in 2013, and the air excavation tools were there, and they actually were able to excavate the majority of the base of the tree. So we can use those tools to really take a better look at the base of the tree. If we weren't going to excavate and we wanted to know where the roots were, we might use something like ground penetrating radar, which can generate an image like this, which maps out the depth and extent and size of the roots. And then moving off the ground, if there's something you can't see well, or in your really big tree, oftentimes, even from a good assessment from the ground, you can only see the bottom of the branches, and you certainly can't see into things like this, the branch unions. So aerial inspections, getting up in the tree, either climbing, which I prefer to do, or using some kind of aerial lift, can be very advantageous in seeing more. We can look at a more complex tree like this with decay and cavities and a whole network of cabling installed in the tree. We can look at, as I mentioned, the tops of branches where this crease and perhaps cavity in this branch couldn't be seen from the ground. We can look more carefully at suspect branch attachments, like this large oak branch on the left side, or another large oak branch which looked perfectly fine from the ground, but actually has a crack and a cavity in it when we see it from above. And then you may also discover that there are critters living in the tree, not just large mammals, but other tree associates. And I think in my conservation arboriculture world of things, trees as habitat is an important thing. And of course, we're only going to see these things if we get up in the tree. So then another aspect of looking at trees as they age is that decay can happen, internal decay, which is hard to detect. So one of the first tools to be proposed for using in that fashion, these are drilling instruments. In the top right corner is an increment core. These are all instruments that were actually designed for something else other than risk assessment of trees. So the drilling instruments were designed for wooden structures, as you can see in some of these pictures here. And an increment core is actually a forest mensuration or measurement tool where we can look at how a tree is growing. The problem with an increment core is that it makes a big hole and causes quite a lot of damage. And if you're trying to find out about a whole forest and you put a couple of holes in some trees, that's not so bad. But if you're looking at one tree, it can be problematic for the tree by putting such large holes in the tree. But we use these drilling tools to find decay in the tree, to find out how much solid wood is there. I think that's a point to emphasize that I like to talk about. I'm not really trying to find out about how much wood is missing. I'm trying to find about how much wood is still there, because that's the wood that's important now. That's the wood that needs to be sound and that is carrying the loads on the tree and that we can use to keep the tree there. The drilling instruments generally, what they're trying to look at is the way they work is as the very fine drill bit is forced at a steady rate into the tree, the instruments measure the resistance to the forward motion of the drill. So here's a graphic from an IML Resi, and it measures sort of the amplitude of resistance, and we see sort of in parts of the graph, we see consistent sort of higher areas, but in the middle, we see these areas where the resistance drops off considerably compared to the rest. And it's those types of areas that we can detect with those tools, areas of decay or cracks, which may indicate internal features of the tree that we're interested in. I mentioned the increment borer. It can also happen with drilling, and one of the principal things which I'm worried about, a few things with drilling. First of all, you have to figure out where to drill, and if you drill in the right place, you'll find a lot of wood, and if you drill in the wrong place, you might find no wood. So we don't really know that from the outside. So that's a challenge. And then the question is, how many times do we drill the tree to find out enough information? And if we start drilling the tree a lot, could that damage lead to a problem? The primary problem that it can lead to is if we have decay in the center of the tree, and we remember what Shigo taught us about coated and compartmentalization. The barrier wall, or wall 4, is the most important one. It keeps decay from moving in the inside of the tree into the healthy wood. And this example is where an increment core was used on a tree to do risk assessment. There were 8 to 10 drills around the tree. And while the tree had a good wall 4 and an intact wall when that was done, by breaking wall 4 into the area of decay, it allowed for the decay to progress, as we can see indicated here. And unfortunately in this tree, and this is the extreme example, but this tree failed at the level where all of that drilling was done. And we certainly don't want to run the risk of doing that when we're trying to, especially trying to keep a tree. We don't want to cause more damage to it. So recognizing some of those limitations, and again, I want to emphasize, I'm not suggesting that every time we drill a tree that this will happen. In fact, there's a lot of evidence to say that isn't true, but it can happen, and it does happen, and if we can avoid it, I think we should. Out of that concern for that type of problem, the next method that I want to talk about is sonic tomography. It was initiated to reduce that problem of breaking the wall 4 barrier. It is not a non-invasive method, but I would describe it as a minimally invasive method, because we do have to tap nails into the wood, but we tap them just lightly through the bark into the sapwood, and the tree has a lot of opportunity to repair and recover and not be significantly damaged by a nail being tapped into it. And certainly if you spend much time with urban trees, you see lots of metal embedded in trees that didn't cause its death. So the idea is that the nails form measuring points. And here's a graphic to describe that. So each one of these dots around the outside is a measuring point, and a measuring point should be a sending point and a receiver. So the way that the methodology works is, if we take this hammer and the hammer strikes one of those nails, it sends a sound wave out through the tree, which you can see moving around here. And the machine measures how long it takes from when that hammer struck to when the sound reaches those other receivers. So we get a dense map of how sound is traveling through the tree. And we take that a bit further. This is the only math I'm going to show you, really, but it's simple math. And velocity on the left side of the equation equals distance divided by time. So if we know how far the sound wave went, which we measure on the outside of the tree, and we know how long it took, which the instruments measure, then we'll know how fast that speed was. So what we end up with in tomography, and it's really important to remember this, is we end up with a sonic velocity map. We do not have a map of decay. We, as arborists, need to interpret what this image is telling us. And this is an image that's generated from the PICUS sonic tomography. There's a few others. And with the PICUS, the color scheme is brown is solid wood, green is some sort of transitional area, and the blue or violet is areas where sound doesn't travel well. It doesn't necessarily mean it's a cavity. In this case, if you look at the actual tree on the right here, you can see that there's some cracks in there. There's advanced decay, there's some early decay, but sound isn't traveling very well in there. And what we do know, as I mentioned before, is that there is a ring of solid wood around whatever is causing the sound to move slowly in the middle. This is just an image from another tomograph from Rintech, and they use a different color scheme, but the technologies use the same approach. So those are methods that we can actually look at the internal condition of the tree and try to quantify the decays that is there. But I would caution that it's only information. Those tools do not give us answers, and they do not give us the likelihood of failure of a part. They give us clues that we need to understand, we need to interpret in the context of the whole tree, the species of the tree, etc., before we can give an opinion about the likelihood of failure. The last advanced method that I'm going to talk about today is what is commonly described as a tree pulling test. It could also be called a statics integrating assessment. And based on my experience and knowledge, this is one of the only methods that actually will quantify the likelihood of failure. And the method was originally conceived by Dr. Lothar Wessely in Germany in the late 80s, early 90s. He worked with a team of other scientists to further develop another method for whole tree assessment that was and is non-destructive. So we can test a tree in this fashion without causing any problems for the tree, but get really good answers about either the stability of the tree, if it's had root problems or you see root rot or it's constrained, or about the breaking safety of the tree if it has significant decay or cavities. So all of the, this comes out of engineering science, statics engineering science. And if an engineer, for example, was going to look at a structure, a building, a bridge, they would be doing statics assessments. And in order to come up with a safety assessment, which would be in the center where all these arrows converge, they need to consider three things. And this is called the triangle of statics. First of all, we need to look at the load that's acting on the load-bearing structure. We need to look at the form or geometry in the left corner here of the load-bearing structure. And we need to look at the material properties of that structure. So if it was a building, material properties might be, wood versus concrete versus steel versus glass. All of those have different properties in terms of, conferring safety to the structure. And we would look at the form or geometry. Is it a hollow tube? Is it a solid column? Is it a square? And then the loads that might be acting on that. With a tree, the load that we're most concerned about is wind loading, acting on the crown of the canopy and creating bending forces at the base of the tree. And those bending forces will either contribute to breaking a tree that has hollowness or significant decay, or it's also the force that could uproot the tree. The form or geometry is how solid or empty is the tree stem that bears that load. And the material properties is material properties of green wood. And the most important one is something called the compressive strength of the green wood, because it's well understood that when wood fails under loading, it always fails in compression first and in tension next. So to just quickly go through the steps of what a wind load assessment might be, or what a tree pulling test might entail. First of all, we use a digital photograph of the tree, and we take some measurements, the height of the tree, the height of the canopy base, the width of the canopy. We also take into consideration a lot of factors with regards to the exposure of the tree, where it sits. Is it in a forest? Is it in a field? Is it next to a lake? Is it in an urban fabric where it's surrounded by buildings and it really doesn't encounter much wind loading? What the analysis does is, if you imagine the tree, here we have 19 increments. These are actually meters. And if you imagine slicing the tree 1 meter at a time, the analysis basically takes the height above the ground, the amount of area that would be exposed to the wind, and the wind speed at that height, and calculates a load. It sums up all those loads and comes up with something called the resistive bending moment. So that is the load that the base of the tree or the roots needs to be able to resist in order to survive under a wind loading event. Then the next step is that we would actually conduct the pulling test. And so here we have a sort of a model of a pulling test. We have the tree, an anchor is set in the tree at an appropriate height. There's an anchor on the ground somewhere, and we have an industrial strength winch. My winch that I use for pulling tests can pull 4 metric tons or about 8,800 pounds. And we have a measuring device, a load cell in the pulling line to measure how hard we're pulling on the tree. We'll also measure the angle of that pulling line to try and correct that load as if it's acting straight on the tree. When we do the pulling test, there's a maximum for inclination that we never pull harder, and that's 1/4 of a degree. And also a maximum compression or tension that we create in the tree of 200 microns. And what that ensures is that under all the pulling tests, we are within what's called the elastic limit of the tree. So the tree will bend, we'll be pulling on it, but it will return back to its previous state without any damage. So it's a non-destructive method. So when we do that pulling test, we can, if we're looking at the condition of the tree inside and whether it has enough strength to resist breaking, we use this instrument called an elastometer, and it measures stretching or tension of the fibers down to a thousandth of a millimeter, so down to a micron. And then if we're looking at whether the tree is going to uproot or not, we have an instrument here that we place right at the very base of the tree called an inclinometer. And what that is doing is it's measuring essentially the activity at the root plate, and it measures down to 100th of a degree. So the idea is that these instruments are very fine, and we can pull lightly on the tree in the non-destructive range of load. And because these instruments are so fine, we collect good measurements about how the tree is behaving. We also know that we can extrapolate those reactions under a low load to how the tree would react under a load. And then we compare that extrapolation to the wind load analysis. Once everything's set up on the tree, you need a good anchor, you need a strong man to pull hard on the tree. At the end, and I know this is a very simplification of this method. So the results that we get in the end are expressed as a safety factor, and a safety factor of 1 means that the tree can exactly resist the load that we calculated in the wind load analysis, but it has no reserves. What we're looking for is actually a safety factor of 1.5 or more, which means the tree passes the test and still has some reserves. If we have a result that's less than 1, oftentimes there's not much can be done about that tree, although there may be, but oftentimes that leads to removal. Trees between 1 and 1.5 generally need some form of mitigation to increase it, and trees that are greater than 1.5, we say pass the test and there's nothing required. So the results are actually presented graphically, like we see here. The division between 1 and 1.5 is at the red to gray zone, and the gray to green is 1.5 or higher. So if we see results like this, where all our results show up in the green area, that's a good tree and passes the test. And we would say, in terms of likelihood of failure, this is improbable. On the other hand, we can, where one of the real life situations where we've applied tree pulling tests is a situation like this, where road reconstruction on sidewalk and curb occurred, and you can see the vast quantity of roots that were affected. When we pull tested these trees, we see the results like this, where the safety factor is well below 1, and regrettably, those root cutting activities left these trees unstable, and they had to be removed. But there's really no other way we could determine that without this type of tree pulling test. So I wanted to get to a couple of case studies as we get nearer to the end of the presentation. The first one is a very interesting tree that we got to work with. It's on the Woodside National Historic Site, and I am from Canada. I live near Toronto, Ontario, Canada, and Woodside is in a community about an hour away. And it's a site where, as you can see here, William Lyon Mackenzie King, who was our 10th Prime Minister, this is the site where he actually grew up and was born. So a beautiful house, and I think I can't remember exactly what portion of his childhood he lived here, but he lived here with his parents. This was his father, and his father was keen on planting trees. And this tree that we see on the right side here is a tulip tree that was planted by the King family at the time that they had residence there. When I was first asked to look at this tree was 2007, I think. And I should say that what I subsequently found out is that this tree has one of the highest conservation designations of any living plant in the National Historic System in Canada because of its intimate connection with our Prime Minister. So like many times when I first was asked to come to see this tree, the manager told me that he'd had 2 arborists in already, and they both said without any hesitation that this tree just has to be removed. When he didn't really want to see the tree removed given its historic status. So what you see here is a twin stem tree. It's lost the top out of one tree, and it's obviously been declining because the bark has sloughed off. But at the very top on the right-hand side here, there was one large and live branch. So part of amazing things about trees, how can you have all the bark sloughing off on most of the stem and still have a live branch all the way up there? So there's a vascular connection all the way down the tree back into the roots that keeps that branch alive. The concern was that if this part fell over, then it would fall possibly onto the historic building, which we see in the upper left. So we were asked to come in and really do a more thorough assessment of the tree. The first thing, and this, you can see the base of the tree here, no bark, maybe some signs of armillaria here. At the very base in this area, there really was no roots left. So the first thing we wanted to do was sonic tomography to find out what the internal condition of the tree was, how much wood was left in this area, and perhaps more importantly, what's the condition of the tree that's still healthy, because if we were going to do a conservation approach, we would want to cable the suspect tree back to the other side. So we did tomography assessments, and we saw, a result like this. One of the nice things that we can do when you see this crack, this yellow line indicates there may be a crack, we can actually in the analysis divide the tree into 2 parts, and we could see when you look at the whole tree, it looks worse. On either side, there was still some pretty solid wood. At the very base, there was, of course, less. We then went and did a tree pulling test, and we wanted to pull this test, pull the tree perpendicular to this fall line, because we had to strap we were going to consider cabling the other part there. And also the target was over here. And also there would be less supporting roots on the side with the codominant stem. So we did that pulling test, and we came up with a uprooting safety factor of 1.2 and a stem breakage of 1.4. So the stem was still pretty strong, but the roots were definitely compromised, and we didn't have that safety factor of 1.5. One thing we are able to do with the analysis is we can actually digitally prune the canopy. And when you reduce the amount of canopy, especially small amounts at the very top, you can certainly increase the safety factor. So we ran that assessment. Then we went and actually started doing a crown reduction. This here is me up in the canopy of the tree doing that crown reduction, something I very much enjoyed. We also installed 2 cables, a very large cable to support the 2 stems, and then a smaller cable supporting that one live branch from above, because if the branch tore off, we wanted to be able to protect people that might be underneath. And that all work was done in 2009, and by happenstance, I went by the site in the winter, this winter, February 2021, And lo and behold, there is the tree. And evidently our methods and our assessment seem to hold some water, because 13 years after we completed the assessment, and I'm sure no further work has been done, tree's still there. Quickly, one more case study. I know I'm probably just going to go slightly over time here, but this is a project that was brought to me by my colleague Matt Logan. It's a huge bur oak tree, Quercus macrocarpa, in the city of Peterborough, which is again about 2 hours away from where I live. This is a Google Street View from the tree. The tree has a diameter of 1.5 meters, and what you will see is this branch right here is a very large branch that's almost like a second stem. And in 2014, that whole branch tore off. It was a very included union. It had inclusions up at the top, and it was a mechanical failure of the tree. So the first advanced assessment was to get up and do a visual assessment. I went up there with Matt, and despite seeing, a big breakage, etc., there was very little decay associated with here. So we had a lot of confidence that the column of wood at this level was still intact and pretty much able to support the rest of the canopy that was there. Matt had some concerns about the base of the tree, and he wanted to do a thorough analysis of this tree. So he did an air spade excavation. We also did a tomograph at the base of the tree. And what we found was this image where you can see a really big ring of solid wood and some, reduction in sonic velocity in the tree. But for a tree of that size and age, it is entirely normal to expect that the center of the tree is non-functional and may be decaying. There was a strange feature a couple of meters up the trees at about 8 or 10 feet, let's say, where there was this sort of horizontal cracking feature. So we did another tomograph there. And similarly, we found even a more solid tree here with no indication of any slow velocity in the stem. The air excavation did reveal some minor decay on the outside. Of course, we didn't have the tomograph image at the time when we were there. There was also some minor decay on the other side. So we did do a pulling test with this tree. These are the inclinometers right at the very base of the tree. And with this tree, the results were 4.1 as the safety factor, way up in the green. And that means that the tree really is 4 times stronger than it needs to be, even under a high wind event. So tree is definitely not going to topple over anytime soon. So here's Matt and Phil Pavey. They brought in this spider lift, and they did what I would call a crown reduction. They trimmed away some of the dead tips and also shortened all of the branches around the canopy. This would definitely reduce the wind loading and hopefully induce some internal growth in the lower parts of the tree. They went, as I mentioned, all around, and every branch was shortened back to a side branch. And this is what the tree looked like after the assessment. And the only other thing that was done, you may be able to see, if you see my cursor, this other large limb attached low and over the house. And as a extra precaution, we installed an 8-ton Cobra cable for the unfortunate circumstance that tree decided to, or that branch decided to give way. It would be covered. So we went through a variety of techniques here and some mitigation strategies and how they were applied. I just want to finish off with a couple of notes about, I mentioned where a lot of this is coming from is conservation arboriculture, looking at how we can keep old and aging trees. And these are some guiding principles from the National Tree Safety Group in the UK. Trees provide a range of benefits to society. I like to say we don't plant trees in our urban environment just to cut them down later, so let's try and keep them. Trees are living organisms which naturally lose branches, and that is for kind of normal for trees. The actual risk to human safety from trees is statistically very low, where we have those statistics. However, a tree owner has a duty of care for their trees. They need to ensure that their trees are safe for themselves, but even more so to other people off their property. And lastly, that the approach to tree management should be balanced and proportionate. So we take into consideration benefits, habitat, some of these safety considerations, and look at that. And let's not be too hasty into what I like to call basal pruning with a chainsaw, or just removing the tree when it looks a little off. Let's give them a better chance. So I like to say, let's not let the sun set on our heritage trees. And I thank you very much for your attention today and the chance, and once again, thank the ISA for the chance to present. And here are some of my contact information in case you care to follow up at some point. I'll be happy to answer some questions. Thanks again.
Thank you for viewing the session. The CEU code for this session is CF21032. Please note that to receive credit for this session, you must have viewed the session in its entirety and submit the CEU form located in the Resources tab within the Whova platform. When submitting the CEU code, please make sure you submit the code in the same format as shown on the screen. If you have any questions on how to submit CEUs for this session, please review the How to Submit CEUs tutorial located within the event agenda.